Good evening, everyone, and welcome to your favorite sleep channel, The Droning Professor. Tonight we're going to learn about why most of space is a vacuum. So, as you make yourselves comfortable, please take a moment to let us know where you're listening from, and feel free to subscribe. Now, as always, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. I'd like you to take a deep breath. Go ahead. Really fill those lungs. Now consider this. In that single breath, you just inhaled approximately 25 sextillion molecules. That's a 2 followed by 22 zeros. You did that without even thinking about it, probably while also checking your phone or wondering what's for dinner. We live in what scientists politely call a dense environment, though anyone who has ever been stuck in traffic might use stronger language. But here's the thing that should keep you up at night, or at least mildly perturbed during your afternoon coffee. You are cosmically spoiled. The air you breathe, thick with nitrogen and oxygen, and the occasional whiff of someone's questionable cologne, represents conditions so rare in the universe that if the cosmos could laugh, it would be absolutely howling at us right now. Tonight, we're going to explore one of the most profound and, frankly, humbling facts about our universe. It is almost entirely empty. And I don't mean empty like your refrigerator at the end of the month, or empty like promises from a politician. I mean empty in a way that defies human comprehension. Empty in a way that makes the word empty itself feel inadequate. Empty in a way that should make you grateful every single day that you exist on this impossibly cluttered little rock we call home. So settle in, because for the next hour and change, we're going to explore why most of space is vacuum, and in doing so, we're going to fundamentally change how you think about existence itself. No pressure. Let's start with what I call the great cosmic joke, which is this. The universe contains an estimated 10 to the 80th power atoms. Written out, that's a 1 followed by 80 zeros. This number is so large that if you started counting right now, at a rate of 1 atom per second, you would die. And then the sun would die. And then new stars would form and die. And you still wouldn't be anywhere close to finishing. Yet despite this incomprehensibly vast amount of stuff, space is still mostly nothing. It's as if you took all the sand from every beach on Earth, scattered it across a volume the size of 1 billion trillion solar systems, and then complained that the beach was too crowded. The observable universe stretches approximately 93 billion light-years in diameter. Now, if you're doing the math and thinking, wait, the universe is only about 13.8 billion years old, so how can we see 93 billion light-years across? Then congratulations, you've stumbled upon one of cosmology's most delightful mind-benders. The answer involves the expansion of space itself, which we'll get to. But for now, just accept that the universe is significantly larger than it has any right to be, much like my cable bill. Within this vast cosmic arena, matter is distributed with all the evenness of a toddler sharing candy. If you averaged out all the ordinary matter in the universe, the stuff made of atoms, you'd get approximately 5 protons per cubic meter. 5 lonely protons, swimming in a cubic meter of space. To put this in perspective, the air in this room contains about 10 to the 25th power molecules per cubic meter. The universe, on average, is roughly 10 to the 25th power times less dense than the room you're sitting in. But even that average is misleading, because matter isn't distributed evenly. It's clumped, hideously, inconveniently, wonderfully clumped. Galaxies cluster together along vast cosmic filaments, leaving behind regions of space so empty they make the average look positively crowded. We call these regions cosmic voids, and they deserve their own moment in the spotlight of our discussion. In 1981, astronomer Robert Kirshner and his colleagues were conducting a redshift survey, essentially mapping the three-dimensional structure of the universe by measuring how fast galaxies are moving away from us. During this survey, they discovered something that made them triple-check their instruments. A vast spherical region of space, approximately 330 million light-years across, containing almost nothing. Originally dubbed the Great Nothing, this structure is now known as the Boötes Void, named after the constellation in which it appears. The Milky Way could fit into this void billions of times over. In a region of space where we would expect to find roughly 2,000 galaxies, there are approximately 60. 60. That's not a typo. If the Milky Way were located at the center of the Boötes Void, we wouldn't have known other galaxies existed until the 1960s. Imagine, no Andromeda gleaming in the night sky, no understanding that our galaxy was one among billions. Just us, alone in the cosmic dark, wondering if anyone else was out there. Astronomer Greg Aldering captured this perfectly when he said that being at the center of such a void would be profoundly lonely. And he wasn't being metaphorical. He meant literally, scientifically, astronomically lonely. The Boötes Void isn't even the largest void we know of. That honor might go to the KBC Void, a supervoid roughly 2 billion light-years across, that our own galaxy may actually be located within. Yes, you read that correctly. We might be living inside one of the emptiest regions of the observable universe, and it's still too crowded for comfortable intergalactic travel. Cosmically speaking, we're the people who complain about population density while living in Montana. But voids aren't anomalies, they're the norm. When scientists calculate how much of the observable universe's volume lies within voids, the answer is staggering, roughly 80%. 80% of the observable universe is made up of these underdense regions where galaxies are few and far between. The cosmic web, that magnificent structure of galactic filaments and clusters that looks like neurons in some impossibly vast brain, occupies only about 20% of the volume while containing most of the mass. So here we are, living in the 20%, congratulating ourselves on existing at all. Now, let's zoom out even further from the grand cosmic structure and ask a more fundamental question. Why is space a vacuum in the first place? After all, if you went back 13.8 billion years to the moments after the Big Bang, you wouldn't find emptiness. You'd find the opposite of emptiness. You'd find everything that ever was or would be compressed into a space smaller than an atom, at temperatures and densities that make the core of the sun look like a pleasant spring afternoon. The universe began hot, impossibly, unimaginably hot. Within the first few minutes of existence, the temperature dropped to a mere billion degrees Kelvin, which was cool enough for the first atomic nuclei to form through a process called Big Bang nucleosynthesis. Protons and neutrons fused to create deuterium, which then combined to form helium. By the time these first few minutes were over, the universe's elemental recipe was essentially set, about 75% hydrogen, about 25% helium by mass, with trace amounts of lithium and beryllium, and absolutely nothing else. This is worth pausing on. Every element heavier than lithium, every carbon atom in your body, every oxygen atom you just breathed, every iron atom in your blood, none of it existed in the early universe. You are made of materials that wouldn't be manufactured for millions, even billions of years. You are, quite literally, made of stellar leftovers, which is either profound or slightly gross depending on your philosophical disposition. But I digress. The early universe was a hot, dense soup of hydrogen and helium, distributed with remarkable uniformity in all directions. So how did we get from that to the vast emptiness of modern space? The answer is gravity. Gravity is patient. Gravity is persistent. Gravity is that friend who always remembers. You owe them $20, except instead of money, gravity collects matter. Even in the nearly uniform early universe, there were tiny fluctuations in density, quantum whispers in the cosmic fabric that said, slightly more matter here, slightly less matter there. These fluctuations were minuscule, variations of perhaps 1 part in 100,000, but gravity noticed. Gravity always notices. Over millions of years, regions with slightly more matter began pulling in material from regions with slightly less matter. This created a feedback loop. More matter meant stronger gravity, which pulled in more matter, which created stronger gravity. Regions that started out just marginally denser became gas clouds, then stars, then galaxies, then clusters of galaxies. And as matter congregated in these gravitational hotspots, the spaces between them became emptier and emptier. The cosmic voids we discussed earlier aren't just places where matter failed to collect. They're places where matter was actively evacuated, pulled away by gravity to join the increasingly crowded party happening elsewhere. Think of it like this. Imagine a dance floor where everyone is awkwardly scattered around, maintaining uncomfortable distances because this is, after all, a middle school dance. Now imagine that a few particularly charismatic dancers appear, and everyone gradually gravitates toward them. Over time, you'd see clusters of people and vast empty regions of dance floor. That's the universe, except the charismatic dancers are concentrations of dark matter, and the dance has been going on for 13.8 billion years, and nobody is having a good time because dancing in a vacuum is difficult. The expansion of the universe adds another layer to this cosmic emptying. Since the Big Bang, space itself has been stretching. Not objects moving through space, but space itself expanding. If you could pause the universe and place two galaxies a billion light-years apart, then unpause, you'd find them drifting away from each other even though neither one is actually moving. The space between them is simply creating more of itself. This expansion means that even as gravity pulls matter into clumps, the voids between those clumps grow larger. In 1998, two independent research teams discovered something even more startling. This expansion is accelerating. Something which we've creatively named dark energy, because we have no idea what it actually is pushing the universe apart faster and faster. Dark energy now accounts for approximately 68% of the universe's total energy content. Dark matter, the invisible gravitational scaffolding that helps form galaxies, accounts for another 27%. Ordinary matter, the stuff made of atoms, the stuff you and I and every star and planet are made of, accounts for a mere 5%. Let that sink in. Everything you have ever seen, touched, tasted, or measured, every object in the entire history of scientific inquiry represents 5% of what the universe actually is. We are rounding errors in the cosmic ledger, marginal notes in a book written in dark ink. And within that 5%, most of it is spread so thin across space that calling it matter feels generous. The average density of ordinary matter in the universe is roughly 1 proton per 4 cubic meters. If you scooped up a cube of average intergalactic space 1 meter on each side, you might find a single hydrogen atom. Might. It's not guaranteed. Compare this to the air you're breathing. At sea level, there are roughly 2.5 times 10 to the 19th power molecules in a single cubic centimeter of air. A cubic centimeter, the volume of a sugar cube. The universe's average is approximately 25 orders of magnitude less dense than what you're inhaling right now without giving it a second thought. Now I need to introduce you to the interstellar medium, which sounds like a fortune teller who specializes in space-themed readings, but is actually the material that exists between stars within a galaxy. Even within galaxies, which are the crowded parts of the universe, space is shockingly empty. The interstellar medium averages about 1 atom per cubic centimeter. That's 10 to the 6th power atoms per cubic meter, which sounds like a lot until you remember that the air on Earth contains 10 to the 25th molecules per cubic meter. The interstellar medium is roughly 10 to the 19th power times less dense than the air in your lungs. This material is far more tenuous than the best vacuum ever achieved in laboratories on Earth. When we pump the air out of a chamber here on the ground, we can achieve what's called an ultra-high vacuum, with pressures around 10 to the negative 10 torr, corresponding to roughly 100 particles per cubic centimeter. That's impressive by human standards. But the interstellar medium mocks us. At 1 atom per cubic centimeter, It's about 100 times emptier than our best laboratory vacuums. And the interstellar medium is the crowded part of interstellar space. The gaps between galaxies, the intergalactic medium, are emptier still. Out there, you're looking at roughly 1 atom per cubic meter. That's 1,000,000 times emptier than the space between stars, which itself is impossibly empty by earthly standards. If you harvested all the gas and dust from a region of interstellar space the size of Earth, you'd barely have enough matter to make a pair of dice. That's not a joke. That's a scientific estimate published in astronomy textbooks. The universe is so empty that you could collect the matter from an Earth-sized volume of space between stars, and the result would fit in your pocket with room to spare for your keys. Let me give you another way to think about this. Suppose you're an astronaut, floating in the void between galaxies, the truly empty parts of space. You're surrounded by an apparent nothingness so complete that if you reached out in any direction, you could extend your arm for 1,000,000,000 years and probably not touch another atom. Probably. Statistics still apply, even in the void. Yet even this intergalactic void isn't truly empty. There are still hydrogen atoms drifting through, 1 per cubic meter or so. There are photons, light from distant stars, cosmic microwave background radiation left over from the Big Bang, still glowing faintly at about 2.7 degrees above absolute zero. There are neutrinos, ghostly particles streaming through all matter as if it weren't there, billions of them passing through your body every second without interacting. There is dark matter, invisible to all our instruments but making its presence known through gravity. And there's something else, something that challenges our very concept of emptiness: quantum vacuum fluctuations. Welcome to my favorite part of this discussion, where physics gets weird enough to make philosophy jealous. According to quantum mechanics, empty space isn't really empty. Even in a perfect vacuum, with every atom and particle removed, space itself is bubbling with activity. Pairs of virtual particles pop into existence and annihilate each other so quickly that they never become real in the classical sense, but their effects are measurable. This isn't speculation. In 1948, Dutch physicist Hendrik Casimir predicted that 2 uncharged metal plates placed very close together in a vacuum would experience a tiny attractive force. Why? Because the virtual particles between the plates are restricted by the boundaries, creating fewer quantum fluctuations between the plates than outside them. The resulting pressure difference pushes the plates together. The Casimir effect was experimentally confirmed in 1996 by Stephen Lamoureau, and it remains one of the most beautiful demonstrations that empty space is anything but. The vacuum itself has energy, has structure, has properties. You could remove every atom from a region of space, and you would still have something: a seething quantum foam of potential particles, a latent energy that permeates all existence. The vacuum energy of empty space is, depending on how you calculate it, either exactly what we observe as dark energy driving the universe's acceleration, or is off by approximately 120 orders of magnitude from what we observe, which is either the worst prediction in the history of physics or a sign that we're missing something fundamental. Physicists are divided on which interpretation to be more embarrassed about. But quantum fluctuations aside, let's return to the question of why space is empty in the conventional sense, and let's approach it from an even more fundamental angle: atoms themselves. Here's a fact that will ruin your sense of solidity forever. Atoms are mostly empty space too. The standard picture of an atom, the one you probably learned in school, shows a dense nucleus surrounded by electrons orbiting like planets around a sun. This model, proposed by Ernest Rutherford in 1911 after his famous gold foil experiment, revealed something startling: atoms are almost entirely nothing. Rutherford directed his students Hans Geiger and Ernest Marsden to fire alpha particles, which are essentially helium nuclei, at a thin sheet of gold foil. According to the prevailing plum pudding model of the atom at the time, which imagined atoms as uniformly distributed positive charge, with electrons embedded throughout, the alpha particles should have passed through with minimal deflection. Most did. But a tiny fraction, about 1 in 8,000, bounced back toward the source. Rutherford famously described his astonishment by saying it was as if you fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. The only explanation was that atoms contained a tiny, dense nucleus surrounded by mostly empty space. The electrons weren't orbiting in a diffuse cloud. They were spread across a volume roughly 100,000 times the diameter of the nucleus itself. To visualize this, imagine the nucleus of an atom as a marble placed at center field of a large football stadium. The electrons would be somewhere in the parking lot. Everything in between? Nothing. Empty space. Void. If you could remove all the empty space from the atoms in your body, compressing only the protons, neutrons, and electrons together, you would be smaller than a grain of salt. All of humanity could be compressed to fit inside a sugar cube. The solidity you feel when you knock on a table, the resistance you experience when you try to walk through a wall, these aren't caused by atoms touching each other. They're caused by electromagnetic forces, by the quantum mechanical properties of electrons refusing to occupy the same space. You have never actually touched anything in your life. The closest your atoms have come to the atoms of another object is about a nanometer, at which point electromagnetic repulsion says no further. So matter itself is mostly empty space, and matter is already incredibly rare in the universe, and the universe is mostly void. Emptiness nested within emptiness nested within emptiness. It's emptiness all the way down. Now, I should pause here and address a nuance that modern physics demands we acknowledge. The statement, atoms are mostly empty space, is, from a quantum mechanical perspective, somewhat misleading. Electrons aren't little balls orbiting the nucleus. They're probability waves spread across the entire atom. The empty space between the nucleus and the electron cloud isn't really empty. It's filled with the electron's wave function, describing where the electron might be found if you looked. In this sense, atoms aren't empty at all. They're filled with the quantum presence of electrons, with electromagnetic fields, with the Higgs field that gives particles mass, with all the fields and fluctuations of quantum mechanics. A physicist might argue that the mostly empty space description is an outdated relic of the Bohr model, a useful but fundamentally incorrect picture that persists in popular science because it's easier to visualize. This is fair criticism. But for our purposes, the classical picture captures something true about the distribution of mass. Yes, the electron's wave function fills the atom, but the mass is concentrated almost entirely in the nucleus, and the nucleus is 100,000 times smaller than the atom it defines. The electrons contribute only about 1/20th of 1% of the atom's mass. If you're asking where is the stuff, the answer is packed into an incredibly tiny space, surrounded by fields and probabilities and quantum strangeness, but not by additional stuff. Let me tell you about another experiment that reveals just how empty matter truly is. In 1956, physicists Frederick Reines and Clyde Cowan detected the neutrino, a particle so uninterested in interacting with matter that it passes through everything as if it weren't there. The Sun produces approximately 200 trillion neutrinos every second, and about 65 billion of them pass through every square centimeter of your body every second. Through, not around. Through. They fly through the Earth itself without noticing it's there. Neutrinos can do this because matter, from their perspective, is almost entirely empty space. The nucleus of an atom is so small compared to the atom itself that a neutrino can thread through the gaps without ever coming close enough to interact. A neutrino could pass through a light year of solid lead and stand a decent chance of emerging from the other side unscathed. This is how empty atoms are. This is how empty matter is. And this is how empty space is, filled with matter this empty, distributed more sparsely still. Let me take you on a little journey now, a thought experiment to help cement just how vast and empty our universe really is. Imagine you're on a spacecraft, departing Earth at the speed of light. This is impossible, of course, but imagination has no such constraints. At light speed, you pass the Moon in about 1.3 seconds. You reach Mars, at its closest approach, in about 3 minutes. The outer edge of our solar system, the heliopause where the solar wind gives way to interstellar space, takes about 17 hours. Now you're in interstellar space, and everything changes. To reach the nearest star, Proxima Centauri, takes 4.2 years. 4 years of travel at the fastest speed the universe allows, and you've barely left the neighborhood. The next 100 stars might take another century or two. The Milky Way galaxy is roughly 100,000 light-years across, so traversing it would take 100,000 years at light speed. And our galaxy is one of roughly 2 trillion in the observable universe. During your journey through interstellar space, how often would you encounter matter? Almost never. At an average density of 1 atom per cubic centimeter, you could travel for millions of miles and encounter only scattered hydrogen atoms and the occasional dust grain. The dust, by the way, averages about 1 particle for every trillion atoms, which means 1 dust grain for every few thousand cubic kilometers of interstellar space. Now, leave the galaxy. Enter the true void between galaxies. Here, even that 1 atom per cubic centimeter density drops by a factor of 1,000,000 or more. You might travel for 1 billion years without encountering a single atom. The light from distant galaxies, red-shifted by the expansion of space, would be your only company. That, and the cosmic microwave background radiation, that remnant glow from the Big Bang, still warming you, barely, at 2.7 Kelvin. In 1965, 2 radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, using a large horn-shaped antenna originally designed for satellite communication. They detected a persistent background noise that wouldn't go away. They checked everything. They pointed the antenna at New York City. They cleaned pigeon droppings out of the horn. Nothing worked. What they had discovered, almost by accident, was the cosmic microwave background radiation, the afterglow of the Big Bang itself. This radiation fills all of space, the remnant heat from when the universe was young and hot and dense. It's everywhere, in every direction, at every location in the observable universe. Even in the vast voids between galaxies, this background radiation persists. So even the emptiest reaches of intergalactic space aren't completely empty. They're bathed in ancient light, in the memory of the universe's fiery birth. The vacuum of space is a museum, preserving evidence of cosmic events that occurred billions of years before the Earth existed. Penzias and Wilson shared the Nobel Prize in Physics in 1978 for their discovery, proving that sometimes the greatest breakthroughs come from noise you can't eliminate. Let's talk about why any of this matters. Why should we care that the universe is mostly empty? First, the emptiness of space is what allows us to see the universe at all. If intergalactic space were filled with gas and dust, light from distant galaxies would be scattered and absorbed before reaching us. We'd see only nearby stars, a claustrophobic cosmic bubble with no hint of the vast structures beyond. The emptiness of space is the medium through which we've learned about the universe, the transparent lens through which cosmology peers. Second, the distribution of matter, clumped into galaxies and strung along cosmic filaments with vast voids between, tells us about the physics of the early universe. Those tiny quantum fluctuations from just after the Big Bang, the ones that seeded the formation of all structure, left their fingerprints on the cosmic microwave background and the distribution of galaxies. By studying where matter is and where it isn't, we learn about conditions that prevailed billionths of a second after time began. Third, the emptiness of space makes interstellar travel theoretically possible. If the interstellar medium had the density of air, any spacecraft traveling at even a tiny fraction of the speed of light would be vaporized by friction. The near vacuum of space means that, in principle, a ship could coast from star to star without burning up. Of course, even 1 atom per cubic centimeter adds up over light years of travel, and designing shielding for such journeys remains a formidable engineering challenge. But it's a challenge, not an impossibility. Fourth, the emptiness forces us to confront our own cosmic insignificance with appropriate humility. We live on a small planet orbiting an ordinary star in the outskirts of an average galaxy in a universe that is 95% stuff we can't even see. And within the 5% we can see, most of it is empty space. And within the matter that exists, most of it is empty space. The universe, quite literally, is not about us. This might sound depressing, but I find it liberating. If the universe isn't about us, then we're free to make our own meaning. We're not the center of a cosmic drama. We're improbable configurations of matter that have somehow developed the ability to contemplate our own existence. That's not insignificance. That's extraordinary. Now let me address a question that might be bothering some of you. If space is almost completely empty, why do astronauts need spacesuits? If there's practically nothing out there, what's the danger? The answer is that the near vacuum of space is precisely the danger. Your body is adapted to exist under the constant pressure of Earth's atmosphere, roughly 100,000 pascals pressing on every square centimeter of your skin. Remove that pressure, and things go wrong quickly. In a vacuum, the gas dissolved in your blood and tissues starts to bubble out, a condition called ebullition. Your saliva and the moisture on your tongue would boil, not because they're hot, but because the boiling point of a liquid depends on pressure. At zero pressure, water boils at body temperature. Your lungs, designed to work against atmospheric pressure, would likely suffer damage if you tried to hold your breath. Air trapped in your body cavities would expand. You wouldn't explode, despite what movies might suggest. Human tissue is elastic enough to contain the expansion, but you would lose consciousness within about 15 seconds as the oxygen in your blood rushed to your brain's aid and then wasn't replenished. You would die, most likely from hypoxia, within a minute or two. The vacuum of space is dangerous not because it contains something hostile, but precisely because it contains nothing. It is the absence of the environment we evolved to inhabit, an absence so complete that our bodies simply can't cope. Let me share one more perspective on cosmic emptiness, and then we'll begin wrapping up this journey through nothing. Consider the scale of time. The universe is approximately 13.8 billion years old. Our sun formed about 4.6 billion years ago. Life on Earth arose roughly 3.5 billion years ago. Complex multicellular life only about 600 million years ago. Homo sapiens a mere 300,000 years ago. Recorded human history spans perhaps 5,000 years. Your lifetime will span, if you're lucky, about 80 years. The universe has been emptying itself for nearly 14 billion years, gravity patiently sorting matter into clumps and leaving voids in between. The accelerating expansion driven by dark energy has been operating for about 6 billion years, pushing those voids ever wider. In the cosmic timeline, we exist in a particular moment, a moment when the universe has aged enough to form stars and planets, but hasn't yet expanded into total isolation. In the far future, cosmologists predict the expansion will continue and accelerate. Distant galaxies will recede beyond the cosmic horizon, their light red-shifted into oblivion. The local group of galaxies, gravitationally bound to each other, will merge into a single massive galaxy, but everything beyond will fade from view. Future astronomers, if they exist, will look out at a sky containing only their own galaxy, surrounded by an empty void that shows no trace of the cosmic structures we can see today. The evidence for the Big Bang, written in the cosmic microwave background and the distribution of distant galaxies, will be erased. The future universe will be emptier than the present one, and its inhabitants will have no way of knowing that it was ever otherwise. We live in a privileged time, cosmologically speaking. We exist in the epoch when the universe has revealed its secrets to careful observers. We can see the cosmic web, measure the background radiation, trace the expansion back to its explosive beginning. Future intelligent beings, if any arise in the cold dark eons to come, may never know what we know now. So, what have we learned tonight? We've learned that the universe is mostly empty by almost any measure you care to use. The average density of ordinary matter in the cosmos is about 5 protons per cubic meter, with the vast majority of space containing far less. Cosmic voids make up roughly 80% of the observable universe's volume. The interstellar medium between stars has only 1 atom per cubic centimeter. The intergalactic medium between galaxies has roughly 1 atom per cubic meter. We've learned that this emptiness is a consequence of the Big Bang and the action of gravity over cosmic time. The universe began as a hot, dense soup of matter and radiation, and gravity has been pulling that matter into clumps ever since, evacuating the spaces between. The accelerating expansion of the universe, driven by dark energy, is making those empty spaces emptier still. We've learned that even atoms themselves are mostly empty space, their mass concentrated in tiny nuclei surrounded by the quantum probability clouds of electrons. The solidity of matter is an illusion created by electromagnetic forces and quantum mechanics, not by particles actually touching. We've learned that even empty space isn't truly empty. Quantum vacuum fluctuations fill all space with virtual particles popping in and out of existence. The Higgs field permeates everywhere. The cosmic microwave background bathes the entire universe in the remnant glow of the Big Bang. Dark matter and dark energy, whatever they are, make up 95% of the universe's total content. And we've learned, perhaps most importantly, that we exist in a cosmically rare configuration. We are improbable arrangements of matter living in one of the universe's crowded neighborhoods, breathing an atmosphere that represents conditions almost never found in the cosmos. The emptiness of space is the rule. Our experience of matter and substance is the exception. There's a story, perhaps apocryphal, about the astronomer Carl Sagan. Someone asked him what he thought about every time he looked up at the stars. His response was something like, "I think about the fact that if you took all the atoms in my body and spread them evenly across the observable universe, there wouldn't be enough of me to be found in any given region." That's the human condition in a cosmic context. We are rare concentrations of complexity in a universe that trends toward emptiness and disorder. We are brief patterns in the fabric of space-time, temporary arrangements of atoms that somehow became aware of themselves. And yet here we are, discussing the vacuum of space, using matter to contemplate the absence of matter, using atoms to think about the emptiness between atoms. That itself is a kind of miracle, one that the empty universe made possible by providing the stable conditions for stars to form and planets to coalesce, and chemistry to become biology, to become consciousness. The vacuum of space isn't something to fear or mourn. It's the canvas on which existence paints itself. It's the silence that makes the music meaningful. It's the absence that defines presence. You will leave this room tonight and step out into an atmosphere so dense with molecules that a single breath brings in more atoms than there are stars in the observable universe. You will feel the weight of air pressing on your skin, the resistance of matter as you move through it. And maybe, just maybe, you'll pause for a moment and feel grateful for all this crowded, cluttered, wonderfully substantive stuff. Because out there, in the vast majority of the universe, there is nothing but darkness and vacuum and the patient ticking of cosmic time. Out there, atoms are so rare they might as well be miracles. Out there, the universe yawns empty and infinite, ancient beyond comprehension, expanding forever into more and more nothing. And here, on this improbable little world, you exist, you breathe, you think, you wonder. That's not insignificance. That's the most remarkable thing in the cosmos. Good night. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.